Now, I want you to look around this room. It seems like a pretty solid place, doesn't it? You're sitting in chairs that feel firm. You're leaning on desks that don't give way. You see walls that look like they've been there a long time and aren't planning on going anywhere. It's all very sensible. It's the world we were born into, the world our senses evolved to handle so we wouldn't walk into trees or fall off cliffs. But I'm going to let you in on a little secret. Your senses are lying to you. They aren't lying because they're mean. They're lying because they're efficient. They give you a shorthand version of reality, so you can get through the day without your head exploding from the sheer chaotic wonder of what's actually happening right under your nose. Let's start with something simple. Take a piece of chalk. To you, it's a white cylinder. It's dry, it's dusty, and it's definitely there. If you break it in half, you have two pieces of chalk. If you keep breaking it, you eventually get down to a tiny speck of dust. Now, your intuition tells you that if you had a sharp enough knife and a good enough pair of eyes, you could just keep cutting that dust until you found the smallest possible piece of chalk. We call that an atom. Back in the day, people thought atoms were like little billiard balls, hard, round, and unbreakable. It was a nice, comfortable picture. But then we started poking at the atom and the picture got very strange, very fast. We found out that the atom isn't a solid ball at all, it's mostly empty. To give you an idea of how empty, imagine the nucleus of the atom. The center part is the size of a marble. If you put that marble right in the middle of a big football stadium, the electrons would be like tiny gnats buzzing around way up in the very highest seats of the stand. Everything in between the marble and the gnats is just nothing. It's empty space, and since everything, the chairs, the floor, your own body is made of these atoms, that means you are mostly made of nothing. Now that brings up a problem. If you're mostly empty space, and the chair is mostly empty space, why don't you just fall right through it? Why doesn't your hand pass through the table like a ghost? You might say, well, it's because the atoms are hitting each other, but they aren't. The nuclei are way too far apart to ever touch. What's actually happening is that the electrons, those gnats in the stands, carry a negative charge. And as you know, like charges repel each other. When you try to sit down, the electrons in your pants are pushing back against the electrons in the chair with a force so powerful that it stops you cold. You aren't actually touching the chair, you're hovering a tiny microscopic distance above it, supported by an invisible field of force. You've been levitating your whole life and just never realized it. But even this gnats in the stadium model is too simple. It's still trying to treat the world as if it's made of little things, little pieces of grit. We like to think of electrons as particles, like tiny planets orbiting a sun. But when we look closer, we find out they don't behave like particles at all. If you fire electrons through a screen with two slits in it, they don't act like little lulls hitting a wall. They act like waves. They interfere with each other. They rip. Imagine dropping two stones into a still pond at the same time. The ripples spread out, and where they meet, they either get bigger or they cancel each other out. That's what electrons do. This is where people start to get uncomfortable. They ask, is it a particle or is it a wave? And the answer is, it's neither. It's something else entirely, something for which we don't have a good word in English. It's a quantum object. When it's traveling, it acts like a wave of probability. It doesn't have a single definite location. It's a bit here, a bit there, and a bit over there all at once. It's only when you interact with it, when you look at it, that it seems to snap into a single spot. It's like a spinning coin. While it's spinning on the table, it's both heads and tails in a blurry cloud. It's only when you slap your hand down on it that it becomes one or the other. Now I know what you're thinking. You're thinking this guy is crazy. This is just philosophy. Give me the facts. Well, the facts are in the mathematics. And that brings us to the part that scares a lot of people, calculus. People see equations on a blackboard and they think it's a secret code designed to keep them out. But calculus isn't a wall, it's a bridge. It's the only language we have that is precise enough to describe a world that refuses to stand still. Think about a car. If you drive 60 miles in 1 hour, your average speed is 60 miles per hour. That's easy. That's algebra. But what if you want to know how fast you are going at one specific frozen instant? At that exact moment, you haven't traveled any distance and no time has passed. So your speed is 0 divided by 0. In school, they tell you that's a sin, but calculus found a way to do it. It allows us to look at change as it happens, in the smallest imaginable slices of time. In physics, we need this because everything is constantly wiggling. An electron isn't just sitting there, its cloud of maybe is shifting and flowing. The equations we use, like the ones you might see in a textbook about quantum mechanics, are just descriptions of those wiggles. We use calculus to track how the probability of finding an electron changes from 1/1000th of a second to the next. We aren't calculating where the thing is, we are calculating how the wave moves. This leads us to a very big idea. If these things act like waves, what are they waving in? When you see a wave in the ocean, it's the water moving. When you hear a sound wave, it's the air vibrating. For a long time, scientists thought there must be some kind of invisible jelly filling the universe that allowed light and electrons to wave through it. They called it the ether, but we looked for it, and it wasn't there. So we had to change our perspective. Instead of thinking about particles moving through empty space, we started thinking about fields. This is one of the most important shifts in the history of human thought. Imagine a field of tall grass. If the wind blows, you see a ripple move across the field. The grass doesn't travel from one side to the other, it just wiggles in place. But the ripple moves. The universe is filled with these fields. There is an electron field. There is a photon field. There is a field for every type of particle we know. These fields are everywhere all the time. They are stretched across the entire room, through your body, and out to the furthest stars. And what we call a particle, like an electron, is really just a little bundle of energy, a little glitch or hump in that field that is vibrating particularly hard. Think about that for a sec. It means there is no such thing as an individual electron that is separate from the rest of the universe. Every electron is just a different peak in the same universal electron field. They are all connected because they are all made of the same stuff. When you move an electron here, the field wiggles, and that wiggle can be felt somewhere else. This is the real picture of the world. It isn't a collection of billiard balls bumping into each other in a void. It's a vast, interconnected web of fields, all layered on top of each other, all vibrating at different frequencies. It's like a giant cosmic symphony, but instead of sound waves, the vibrations create matter and light. But wait, it gets even weirder. If particles are just vibrations in a field, what happens when the field isn't vibrating? What happens if we take a region of space and remove all the particles? We call that a vacuum. We call it empty. In the old days, we thought a vacuum was like a stage after the actors had left. Just a quiet, dark, empty box. But quantum mechanics tells us that's impossible. You see, there's a rule in nature called the uncertainty principle. It says you can never be perfectly sure about certain pairs of things. For example, you can't know exactly where a particle is and exactly how fast it's going at the same time. If you pin down the location, the speed gets all fuzzy. If you measure the speed, the location disappears into a blur. There's another version of this rule that applies to energy and time. It says you can't know exactly how much energy is in a system if you're looking at it for a very short amount of time. And empty space is a system. If the energy in a vacuum were exactly zero, if it were truly nothing, then we would know the energy perfectly. And nature doesn't allow that. So the fields can never truly be still. They have to jitter. Even in the deepest, coldest, emptiest part of outer space, the fields are bubbling with activity. They are constantly tossing up tiny bursts of energy. These bursts create pairs of virtual particles, an electron and its opposite, a positron, that pop into existence out of nowhere, live for a trillionth of a second, and then slam back together and vanish. Space is not empty. It's a seething, boiling cauldron of activity. It's like looking at a distant ocean from an airplane. It looks smooth and still, but if you could zoom in until you were right on the surface, you'd see it's a chaotic mess of splashing waves and foam. That's what nothing looks like when you get close enough. Now, why does any of this matter to you? It matters because it changes what you are. You aren't a solid thing in a world of solid things. You are a complex, beautiful interference pattern in a set of fields that have existed since the beginning of time. Every atom in your body is a little knot of energy in a field that spans the cosmos. When you look at a star, you aren't just seeing a distant object. You are feeling the vibrations of the photon field that was started by the motion of electrons in that star. Millions of years ago, those vibrations traveled across the empty space, which, as we now know, wasn't empty at all, and finally hit your eye, causing the electrons in your retina to wiggle in response. It's all one big connected dance. We use calculus to try and map the steps of that dance. We use experiments to try and hear the music. And every time we think we've figured out the rhythm, nature throws a curveball at us and shows us something even more spectacular. So the next time you look at the solid world around you, try to remember the truth. The solidity is a trick of the light. The silence is actually a roar of quantum activity.
The emptiness is full to the brim. It's much more exciting to live in a world like that, don't you think? A world where nothing is actually a fountain of something, and where you are never truly separate from the rest of the stars. We're just scratching the surface here. To really understand how these fields talk to each other, how light hits matter and how electricity works, we have to go deeper into the theory of quantum electrodynamics. It sounds like a mouthful, but it's really just the story of how wiggles in one field cause wiggles in another. It's the most precise theory we've ever had. It allows us to predict things with an accuracy equivalent to measuring the distance from New York to Los Angeles within the width of a single human hair. But even with all that precision, we have to remain humble. We have to remember that our models are just that, models. They are the best stories we can tell with the tools we have. Nature doesn't have to follow our logic. She doesn't care if we find her weird or impossible. She just is. And our job, our great privilege, is to keep looking, keep asking questions, and never be satisfied with the easy answer that what you see is all there is. Because it never is. I want to leave you with one thought for now. If you take away all the stuff in the universe, you don't end up with a void. You end up with the potential for everything. The vacuum isn't the end of the story. It's the beginning. It's the background hum of existence. And everything you see, every person you love, every mountain you climb, every thought you have, is just a momentary ripple in that eternal hum. Now take a deep breath. Feel the air in your lungs. Think about the trillions of atoms, those little field vibrations, dancing around inside you. You're part of the most magnificent show in town. And the best part, we're all invited to watch, if we just know how to look. We'll stop there for today. In the next part, we'll talk about what happens when these fields get really pushed to the limit. When we look at the heart of the sun, or the beginning of the universe itself, we'll see how these virtual particles we talked about can become very real, and how the nothing that doesn't exist actually shaped everything that does. It gets even stranger from here, I promise. But for now, just go out and look at the world. Try to see the wiggles. Try to feel the feel. And don't let the solidity of the sidewalk fool you on your way home. It's all just a very convincing illusion, and you're part of the magic. Now I hope you had a chance to walk around outside and think about those wiggles we talked about. It's a lot to take in, I know. It's hard to look at a solid brick wall and remind yourself that it's actually a shimmering, ghost-like collection of fields. But that's the beauty of it. The world is much more interesting than it looks on the surface. We left off at a pretty strange place. The idea that a box containing absolutely nothing is actually full of activity. I want to dig into that because it's the key to understanding why the universe exists at all. If nothing was actually empty, the universe would be a very boring, static place. But nothing is restless. It's got an itch. To understand this itch, we have to talk about how fields interact. We mentioned that there are different fields for different things. One for electrons, one for light, one for quarks, and so on. But they don't just sit next to each other like neighbors who never speak. They are constantly talking. They are overlapping. When an electron moves, it tugs on the electromagnetic field. That tug travels through the field as a wave of light. This interaction is what we call quantum electrodynamics, or QED for short. It's the jewel of physics, because it explains almost everything you see in your daily life, from why the sky is blue to how your toaster works. But there's a catch. When we try to use our fancy calculus to calculate these interactions, something funny happens. The math starts screaming at us. It gives us answers like infinity. Now in physics, infinity is usually nature's way of saying, you're doing it wrong, try again. If you ask a theory how much energy is in a tiny point of space, and it says infinite energy, you know you've missed something. It took us a long time to realize that the problem was our definition of a particle. We were still trying to think of an electron as a tiny mathematical point. But a point has no size, and if you have a charge at a point with no size, the math blows up. We had to fix the math, a process we call renormalization. It sounds like a fancy word for cheating, and some people, including myself at times, felt that way about it. But what it really means is that you can't look at a particle in isolation. You have to look at the particle plus the cloud of virtual particles it carries around with it. Remember those pairs of particles that pop in and out of existence in the vacuum? Well, they don't just happen in empty space. They happen all around an electron too. The electron is constantly surrounded by a swarm of virtual photons and virtual pairs of electrons and positrons. It's like a celebrity trying to walk down a crowded street with a mob of fans and photographers surrounding them. You can't just see the person. You see the whole commotion. This commotion, this vacuum polarization, actually changes the properties of the electron. It changes its charge and its mass. When we measure an electron in a lab, we are measuring the clothed electron, the one with all its virtual fans. When we accounted for this in our equations, the infinities vanished. The math started giving us numbers that matched our experiments perfect. This tells us something profound. Even a single particle is a collective effort of the entire vacuum. You can't have stuff without the nothing that supports it. Now let's go back to that empty box. If the vacuum is seething with virtual particles, why don't we see them? Why don't they just pile up until the box is full? The reason is that they are virtual. They are like a check that hasn't cleared the bank yet. They borrow energy from the future, exist for a tiny fraction of a second, and then have to pay it back immediately by disappearing. They are a fluctuation, a jitter. But, and this is a big but, if you give them enough energy from the outside, you can make them real. Imagine you have a very strong electric field, something incredibly powerful. If that field is strong enough, it can grab a virtual electron and its virtual positron partner before they have a chance to annihilate and pay back their energy debt. The field pays the debt for them. Suddenly you have two real particles where there were none before. You've turned nothing into something just by shaking the vacuum hard enough. This isn't just a theory. We see this in high-energy particle accelerators all the time. We smash particles together, creating huge bursts of energy, and out of that energy, dozens of new particles are born. They weren't inside the original particles like seeds in an apple. They were created from the fields. This brings us to the biggest question of all, the beginning of everything. If you go back far enough in time, the entire universe was incredibly hot and incredibly dense. All the fields were vibrating with unimaginable energy. In that state, the distinction between nothing and something didn't exist. Everything was a fluid, boiling soup of energy. As the universe expanded and cooled, the fields settled down. Some of the wiggles became trapped or frozen into the stable patterns we call matter, protons, neutrons, and electrons. You are quite literally a piece of the vacuum that got caught in a stable vibration as the universe cooled down. But wait, there's more. We've talked about electrons and light, but there's another player in this game: gravity. Gravity is the ultimate field. According to Einstein, gravity isn't just a force like magnetism. It's the very shape of space and time. Imagine space-time as a giant trampoline. If you put a bowling ball on it, the fabric curves. If you roll a marble nearby, it follows the curve. That's gravity. But if space-time is a fabric, and quantum mechanics tells us that everything must wiggle, then space-time itself must wiggle. This is where things get really hairy. We don't have a perfect theory for this yet. We call it quantum gravity, and it's the great whale that physicists have been hunting for decades. If space-time wiggles at a very small scale, it means that at distances much smaller than an atom, space might not even look like space anymore. It might look like a quantum foam, a chaotic churning mess, where time and direction lose their meaning. At that scale, the illusion of a smooth, continuous world completely falls apart. So why does this matter for our daily life? Because it reminds us that the world is a much more fragile and dynamic place than it seems. We think of the laws of physics as being written in stone, but they are really just the average behavior of trillions and trillions of quantum events. The reason the sun shines is because of quantum tunneling, a process where particles cheat by passing through energy barriers they shouldn't be able to cross. They basically borrow existence from the vacuum to get to the other side. Without that quantum cheating, the sun wouldn't burn, and we wouldn't be here. I like to think of the universe as a giant, cosmic onion. You peel back one layer, the world of solid objects, and you find atoms. You peel back the atoms, and you find nuclei and electrons. You peel those back, and you find fields. You peel back the fields, and you find the seething vacuum. And at every layer, the rules of common sense change. What seems impossible at one level is mandatory at the next. One of the most beautiful things about this is that it takes away the loneliness of the universe. If you think the world is made of separate bits of matter floating in a cold, empty void, it can feel pretty bleak. But if you realize that the void is actually a living, breathing part of you, that you are a wave in the same ocean as the furthest galaxy, then the universe feels like home. There is no such thing as empty space between you and me. We are connected by 1,000 different fields, all whispering to each other in the language of calculus. Now some people get upset when I say the world is an illusion. They think I'm saying it isn't real, but that's not it at all. A rainbow is an illusion in the sense that there isn't a physical arch of colored wood sitting in the sky. It's a result of light hitting water droplets at a certain angle, but the rainbow is still there. You can see it, you can photograph it, and it follows very specific laws of physics. Understanding how it works doesn't make it disappear, it makes it more beautiful. It's the same with reality. Knowing that this desk is mostly empty space and vibrating fields doesn't mean I can't put my coffee on it. It just means I appreciate the coffee and the desk a lot more. I appreciate the incredible balance of forces that allows that cup to stay put. I appreciate the fact that the nothing inside the atoms is doing such a good job of pretending to be something. As we move forward in our studies, we have to learn to be comfortable with this double vision. We have to be able to see the world as it appears, solid, predictable, and simple, while never forgetting the crazy, bubbling reality that lies beneath it. We use different tools for different levels. We use simple mechanics to build a bridge, but we need quantum field theory to understand the electrons that hold the steel together. The math we use, like the Dirac equation or the Schrödinger equation, isn't just a bunch of squiggles on a board. It's a way of navigating a territory that our eyes weren't designed to see. When you look at those symbols, don't see them as obstacles, see them as a special kind of eyeglasses that let you see the wiggles in the vacuum. I often get asked, what comes next? What's the next layer of the onion? And the truth is, we don't know. We might find that fields are made of even smaller strings, or that the whole universe is a projection from a lower dimension. But that's the fun of it. If we knew everything, we could all go home. The excitement comes from the fact that nature always has another secret up her sleeve. But for today, I want you to walk away with this. The next time you feel like the world is too much, or that things are too complicated, just remember the vacuum. Remember that even in the darkest, emptiest parts of your life, there is an infinite amount of energy and potential bubbling away. You are never truly empty. You are never truly nothing. You are a masterpiece of the quantum fields, a unique vibration in the cosmics. And when you look at someone else, remember that they are made of the same fields, the same wiggles, the same vacuum. We are all different notes, played on the same guitar string. That's not just a poetic thought, it's a physical The nothing that doesn't exist is the very thing that binds us all together. So don't let the surface of things fool you. Don't be satisfied with the shorthand version of reality. Keep looking deeper, keep asking why, and most importantly, keep enjoying the show. It's a magnificent, confusing, beautiful mess, and we are the only part of the universe that has developed the ability to stand back and wonder at it. We've covered a lot of ground. We've gone from solid chairs to maybe clouds, from empty boxes to seething cauldrons, and from basic algebra to the heartbeat of the universe. It's a long way to travel in one lecture, but I think you've got the hang of it. You don't need to memorize the equations yet. You just need to keep that sense of wonder alive. When you leave here, I want you to look at the world differently. Don't just see things. See the interactions. See the light bouncing off the leaves. That's the photon field talking to the electron field. Feel the weight of your feet on the ground. That's the curvature of space-time holding onto you. And remember that underneath it all, the vacuum is dancing. The illusion is strong, but now you know how to see through it. You know that what you see is just the tip of a very, very deep iceberg. And the best part, the deeper you go, the better it gets. The world isn't just what's really there. It's everything that could be there, and everything that is trying to be there, all at once. We'll pick this up next time. We'll talk about how these fields create the forces of nature, how they push and pull on each other to build galaxies and DNA. But for now, just go out and be a part of the field. Go be a stable vibration in a beautiful world, and don't worry too much about the nothing. It's doing just fine on its own.